So let me start with the second half of this class on networks and quantum gravity, and today we will finally talk about networks, and as Tom and Alfredo were saying coming here, we will find out if and how we are cut into small pieces at the grand scale, or whether some continuity survives. Because if I manage, today I would like to show you also the first example of a quantum geometry operator that gives a discrete spectrum, and therefore this kind of pieces property. So, by the end of last week, I hope I motivated enough the fact that we would like to use Wilson loops as fundamental quantity states. But let us remind first of all, why did we come to this? Because we said that we had a formulation of generativity that used an SU2 gauge connection as fundamental variable. In particular, the phase space was exactly the same phase space that appears in the study of SU2 Young-Mills theories, with this Poisson bracket in particular, and the only maybe difference you have to pay attention is that this is a density object instead of just being a vector. And we related, I'm going to write again these equations because I'm going to use them. We related these variables to the original method variables, introducing the Ashtekar-Barbero connection, and this is the densitary style given by the determinant of the triad and the inverse triad, and could be written also using the inverse formula determinant in this form here. Now, using Wilson loop's variables, or more in general, cylindrical functions, so we switch from a representation in terms of connection to cylindrical functions. Namely, we look at functionals of the connections which are of a special type. They only depend on the connection through some finite number of holonomies, and each holonomy was associated to some link, oriented link, and there's a finite number of holonomies. Let's say capital L is the total number of links that I'm considering in general. They can be connected by nodes, they can be disconnected, it doesn't matter. We go to cylindrical functions because they depend on the connection only through these holonomies. And I motivated this because one natural gauge invariant, so Wilson loops, so this G, or I mean also these functionals will give rise to another gauge invariant description. When the link was just a closed loop, it's enough to take the trace. Today we will describe more in general how we obtain gauge invariants out of these states. And the second motivation was Beckman independent scalar product. And this was based on using the R measure. So, now that I've recalled what we did on Friday, let us come back to this point and let us talk about quantum theory. Quantum theory, as we all know, is based on choosing some fundamental variables for the classical theory and then seeking a space of square integral functions over which we can give a representation of this algebra as operators. Now, representing the fundamental Poisson algebra as operators works directly when we're doing quantum mechanics. When we're doing quantum field theory, things are slightly more subtle because you don't get operators directly, you get operator value distributions. The operators are only associated with smearings, of the fundamental fields. So traditionally what we do in quantum field theory is that we use three-dimensional smearings. Namely, if this were a Young-Mills theory, I would define my operators as E, for instance, would be first of all I would smear it. So if you were a Young-Mills, I don't need to put the tildes because the notion of densities in space-time that I explained is trivial. I could take a test function. Lambda would have, let's say, compact support, for instance, and I would define such a smearing quantity, such a smeared quantity, which is called the smeared function. And this is how you compute Poisson brackets in a more precise way. Because if you compute Poisson brackets using just this distributional expression, when you have things like the curvature, that depends on derivatives of A, then you have derivatives of delta functions, you have to be careful with signs. If you smear everything, you can do calculations straightforward. So already classical is important possibilities, but quantum mechanical is actually necessary because it is E lambda that is an operator. And not E of x, which is rather what is called the operator value distribution. Now, this is what we do in quantum theory, such three-dimensional smearings. However, the idea of working with quantum gravity is to use Wilson loops and therefore consider smaller, so to speak, smearings. Instead of three-dimensional smearings, we are seeing that the Wilson loop takes into account a line integral of the connection.
Sorry.
Hello? Too far away? Can you hear me?
No, it's all done.
Oops. Sorry. Do you want me to very quickly repeat all this? Okay.
There are some microphones here, so maybe there will be some.
Okay. Anyway, it was more just recalling what we did last week. Okay, so you see that now these holonomies, so now we switch attention to holonomies, and these are 1D smearings of the connection. Because recall that before taking this path-ordered exponential, that's just a line integral. So what I mean by that, if I restore these indices here, I have this line L. Let's say I choose some parameter S that goes from 0 to 1, and then I have a tangent vector. Let's call it gamma A of S, which is given by dxa over ds. So this is the tangent vector to the line or curve, to the curve. I'm using L not really for line, but for link, because when I'm, at the end of the day, I'm using graphs, these will be links of the graphs, and I don't want to have to change notation every time. So that's why I'm using L now. So what this line integral is the integral on ds of this one form contracted with the tangent vector, and now that I've written ds is 0 and 1. And then there's this index I. This is an element in the algebra. What I mean by this index I is the vectorial index in the adjoint representation, and so here I will have the generators. So these are matrices in whatever representation you want to work in. For instance, in the case of SU2, for such generators, we would take the Pauli matrices. The I is to have anti-Hermitian generators, and the factor 1/2 is just standard normalization, so to have, you know, that tau I, tau j is I, epsilon I jk, tau j. Okay? So this is our, so you see this is a smearing already of the connection, and it's a very geometric smearing because the connection is a one form. And so the integral of one forms on lines is actually naturally well defined, no need to introduce a background metric structure or anything like that. Very good. So that's going to be our choice of fundamental variable. Let's see if we can make this work and still get a representation of that algebra.
Can I ask?
Sure.
This is not holonomy.
No. You're right. The holonomy now would be, path order of the exponential of this. So let's say that the holonomy involves one dismeetings of the connection. But of course, what I have to do for the holonomy is this.
Actually, I would be worried about this integral because it is not well defined in the spectral index.
Let's talk about which vector index? This?
Yes.
Right. So imagine that this was an abelian theory to begin with. There is no such index. Okay. Now that this is an abelian theory, this is a matrix, right? So this is the way this line integral here is defined. But we already know that this path ordering, what it's doing, is actually not taking. This is what we discussed when we introduced this path ordering on Friday, right? So in fact, what's happening here is not that I'm taking this line integral and I'm exponentiating it, because it wouldn't satisfy the convolution property. So absolutely, yes. This is just to give you an idea of what is the smearing that is behind. So how about the E field now? The E field, as you can see, is a two-form. Remember that this notation with capital E I'm using is related to the fact that the four-dimensional tetrad, I'm writing it as something like this. N, okay, I don't remember now, somewhere there's a 0. So let's say that this is the line, that this is row, and this is the column, and then it would be the other way around. I think it's something like this. And here, the spatial part, I should check which convention between lines and columns I'm using, but it's one of the two. One is 0 because we're using the time gauge, remember? Namely, that the 0 component is aligned with the normal, which is then lapse dt. That's why one of the two is 0, the other one is, and the rest is lapse and shift. And the 3D part, I'm using capital E instead of little e, just to avoid any confusion. But anyway, all of this to say that this is a two-form. You see there's this epsilon. So if you want, you could also use some shorthand notation and say that E is a Hodge dual of E wedge E. And then there's a second Hodge dual also for the internal indices. So if I put it down, I would say, I would write something like this. This would be the 3D Hodge dual. So it's a two-form. So we can play the same game that we played for the connection. We can naturally smear it on surfaces. And remember that if we were in Yang-Mills theory, this would be the electric field, the non-abelian version of the electric field. So if you integrate the non-abelian version of the electric field on a surface, you get the flux of the electric field. So that's why this second smearing we are going to do is called the flux. So we're going to introduce some surface, just like here we introduced the sum line. Now we're going to introduce some surface. Where is I? Sorry, down. And then we're going to integrate. So let's choose some coordinates on this surface, sigma A, where A is equal to 1 and 2. And then I integrate in the sigma E, A, I, and then these two surfaces, the volume, the area form to integrate on this surface can be characterized in terms of, let's say, the normal, one form of the surface, n, and that's what I need here. So this is smeared flux. So you see that again, it doesn't require any choice of background. This one form comes, it's the definition itself of the surface. So if you want, if this sigma are the coordinates, then the tangent vectors to the surface are given by dxa over d sigma a, dxb over d sigma b, epsilon ABC. That's the definition of, well, I will need to take the antisymmetric combination here. So let's say 1/2 epsilon AB. This is the normal one form. Or if you prefer, you just pick 1 and 2 here, and you can remove this epsilon. Okay, this epsilon is just 0, 1 minus 1, 0. Okay, so standard definition of a norm. Yes?
Do we use automatically closed surface, or how do you?
No, this is open. For the time being, this is open. So this just here. For the time being, this is open. I'm just classically smearing these things.
And here I also have some worries about this index I. And this index I lives in the some.
That's right. Absolutely. Yeah. That's right. For the time being, this index I am leaving it. Okay, very good. So, yeah, you can do two things. Either you ignore the presence of this index I, and then you define something that, as you're already pointing out, is not very covariant. So if you want to be more careful, there are two. I wasn't planning on being so technical, but since you're asking the question, so in fact, you might worry about that, and then you might say, okay, wait a second, let me be more precise. Let's say that not only I have the surface here, okay, so for Pavel, one can also introduce something called covariant fluxes. So now we choose also some point, x, doesn't matter where it is. This is our S. And then for each point on the surface we want to integrate, we choose a path that connects that point to our chosen x. Okay? Now, on all such paths, I have a notion of gauge connection. So whatever is E here, I can always parallel transport it there. So you can define the covariant flux, let's say C, as, so now it will depend on more than just S. It will depend on S, choice of starting point, and choice of set of paths a priori. And then this will be given by the integral of d2 sigma, and then the adjoint action of all your parallel transports from X and your choice of paths acting on E, I, and A. So the good news is that if we want to talk about the fundamental algebra of the quantum theory, you will see that we don't have to, well, we'll have to do, we can simplify things, we can work with these and do calculation once. Okay, let me explain in a second. That's true. If you want to do things fully covariant, you have to go that way. Now, how about the full Poisson brackets? We looked at the, no, actually I haven't looked at any Poisson brackets yet. So how about the Poisson brackets now? If we do these mirrings. First of all, notice that we're doing, it's a three-dimensional Dirac delta we have there. And I'm doing smearing of A in 1D, smearing of E in 2D. Total is 3D. So you might expect that unless there is some degeneracy in these directions, that might be enough. Barely enough. Usually we do 3D smearings and 3D smearings. Now we're doing just 1 and 2. But it might be enough. So let's see. For instance, what would be the Poisson bracket now between H on some line and the flux on some surface? And let me, to begin with, work with this non-covariant flux. One way to reduce the worry that Pavel might have, let's imagine that this surface is infinitesimally small, and at this point x is taken inside the surface, so that somehow I can neglect the effect of this parallel transport for the time being. We will come back to it. Then we can immediately distinguish different cases. There's a Dirac delta. So if there's no point in common between this surface and this path, then the Dirac delta will have no support. So the result of this calculation will immediately be 0 if L intersection with S is empty. How about the other cases? Well, for the other cases, we should just do some functional derivative. So imagine that we had that line element like that. If I do functional derivative of such line element, I will come back to the second, to the fact that there's the path ordering. But let's imagine it was abelian. So I'm just computing something like this. B, and then to J, maybe this to J is one-dimensional because it's abelian. Then by definition of the functional derivative, this gives me just Kronecker and Dirac deltas. And therefore the result is some delta 3 of the point, x prime, let's say. X prime gamma S, namely the point X has to lie on L, otherwise again I get 0, and then gamma A to I, just the Kronecker deltas. Because of the path ordering, this is going to happen pointwise, and you remember that the role of the path ordering was to guarantee the convolution property. Namely, that if I combine path 1 with path 2, H1 group multiplication H2 is equal to H12. So the result of applying the functional derivative to something with the path ordering is that you break that structure in half, in two, and you intervene only at that point where this generator comes down from the exponential. So the result is numerical factor. No numerical factor, so just the integral between 0 and 1 ds of H0s delta of then I have to also integrate, okay. Let me not write the result yet. Let me do it in two steps. So first of all, now we want to do d over dix on the path order exponential, and this I'm telling you is going to give integral between 1 and ds, h between 0 and s, and then that structure, delta cube x gamma s to what is it? I, and then HS1. I'm not computing it, notice. I've just given you kind of an heuristic argument of why this is true. If you want to prove that this is true, you have to use the definition, the explicit definition of the path integral I gave you, you remember, as an infinite sum, as an infinite series. You take the derivative of that infinite series, you see that you reconstruct this. And I'm, of course, forgetting gamma dot. Doesn't matter where I put it, that's just a C number. Let's put it here. But you see, it's acting, it's breaking the holonomy in two and inserting a generator there. So this action, it's called the grasping action. We have this link, and we're now inserting a generator at the point x.
How just it will be now, it seems that this line is touching this Okay, it's a line in the center.
That would be my other case. It's going to be 0 again. You're about to see in a second why.
Okay.
In a second, really, we'll see why. Because now that I have this intermediate step, what I have to do now, the last thing I have to do is to add the integral. Okay, maybe I should have said, I'm realizing I'm giving something for granted, that the definition of Poisson brackets is functional derivatives, right? Sorry, maybe I should have been more explicit. What that means is that fg is the integral of df over d with sine A minus, the swap of f and g. Okay, so that's why okay, so now I have the connection and the smeared field and the smeared electric field, and I'm using this formula. So when I used now the functional derivative acting on the smeared, the non-covariant one to begin with, because I said let's keep things simple, you see that what's going to come down is just the integral in d2 sigma, and then that unit norm n. So when I add also that other piece of information, the fact that I have to integrate over the surface, I end up with integral over the surface. And now we will be able to see all the various cases. Integral over ds, delta q, the Dirac delta, between the link and the positions. X now will have to be part of the two surface, because otherwise I will get 0 from this functional derivative here. And then I have what? Gamma dot n a h 0s to I h s1, and that I is this I here. So now we can see all various cases, because of course if there's no point in common, then there's no support for this Dirac delta, and so you get that 0. If it lies entirely on the surface, look what's happening here. It's a scalar product between the normal and the tangent vector. But if it lies entirely on the surface, this is also 0. So if it lies entirely on the surface, it's also 0. So if L is contained in S, we also have 0.
And then you can have some infinite number across.
Sure, sure.
What's up, man? Yes.
Absolutely. And now I'm going to have, in fact, so, good point. Let me assume, for making this calculation, let's assume that, assuming that the intersection is countable. So you start seeing this very good remark that unfortunately some mathematics will be relevant in constructing the theory. Because if you allow for a class of graphs that is too wild and that, for instance, can intersect in an uncountable way the surface, then you aren't able to do such calculations. So we already start to see that some mathematical assumptions are necessary, this is clear. The point is that when it becomes too sophisticated or too delicate, then one should be worried. Here, so far, to me, it seems like a fair assumption, and we are going to use it in computing the spectrum of the area. So, so if that is the case, then we get this result, well, now, if that is the case, in fact, what you can prove is that this thing just gives you plus or minus 1 for each puncture. So, plus or minus 1 for each puncture of S by L, where the sign depends simply on the relative orientation between the orientation of sigma and the S. So for instance, let's say that, S is oriented like this. What that means is that the normal is outgoing as opposed to being coming. And then there's a relative orientation between such N and the orientation of gamma, which is, puncturing. So let's say if gamma is oriented like this, that means it goes in the same half space as the outgoing normal to S, then the sign is plus by convention and minus the other way. Okay, so that's just...
You're saying that it must be the factor is 1?
Yeah, but you can prove the factor is 1 because you can prove that you get just the Jacobian of the change of coordinates. And this is going from 0 to 1, and this is also going from, let's say, I choose these coordinates such that this is...
What is written in Flux it depends on the angle of...
It depends on?
Angle between these two rectangles.
Why it doesn't depend on that?
That seems that it is imaginary.
I think it does depend on that because it just gives the Jacobian of the change of coordinates. Because you see, let's see what happens. These, gamma A is dxa over ds. And N is epsilon ABC, let's say d sigma 1, d sigma 2. And so basically what should happen is that, so that scalar product then, you see that is epsilon dxa, right. So because of the non-degeneracy condition, I can choose locally S sigma 1 and sigma 3 as a coordinate system. And so what I'm computing here is doing that. So now this becomes a partial derivative because by my assumption I can choose that as, so this is the Jacobian of going from X to S and sigma. Yeah, but this is important. Okay, so basically at the end of the day, we get something like plus or minus, so let's say orientation of the sum over the punctures, or I don't know what to say, minus 1 to the OP, the orientation of the puncture, and then H0 location of the puncture, sorry, I will have to, right, location of the puncture to IH SP1. There are two, so this, it's complicated because we are splitting the holonomy and making graspings, but of course you can imagine that there are simple cases, and the simple cases is when the intersection is just at the source of the link or just at the target of the link. In those cases, so this is if countable number of punctures, and the simplest cases are when it's the source and target. Now, when it's the source and target, typically by conventions we have to put a factor 1/2. Why? Because it means that we're integrating this delta function, and the delta function has support on the boundary. When the delta function has support on the boundary, you put a factor 1/2 by standard regularization, so that might be a bit annoying, but that's the way it is. And now, also we can fix this sign. Let's say because it's source, let's say that this would be sign plus and that would be sign minus. So when is the source, we're gonna have 2, and then we recover H, because now it's acting only at the source, and there would be minus H to I. So this is if L, S coincide with the source of L, and this is if L, S coincides with the target of L. And now look at these special cases here. You should recognize something. Remember, these were precisely pieces of the cotangent algebra of SU2. Remember the right and left invariant vector fields. So this part is same as left and right invariant vector fields that we discussed on Friday. Okay, but how about E now? So now something funny happens that will finally make us talk about the issue of covariance. So maybe I can erase this. Because now we can ask, okay, so I've just computed these Poisson brackets by brute force by computing the functional derivatives. What should happen now to the rest of the algebra? You know, one thing that we insisted on that was very important is that the connection commutes with itself, because otherwise there's no connection representation at the quantum level that we can easily construct. So can we still have that? Well, one thing you have to take into account is that algebra is a canonical algebra. It's an example of canonical commutation relations. This is not. You see, this is not a canonical commutation relation. On the right-hand side, you would have 1. Here, this is a nonlinear algebra. On the right-hand side, you have the element again. Now, first of all, this is fine because it simply means that it's capturing the group structure. And as I've argued, this is the same algebra that appears in lattice gauge theory. But Chris Isham, back in the 70s, when people were trying to understand how to quantize gravity, had already pointed out something very interesting, that, you know, we say that this is the CCR, canonical commutation relation algebra, and this is what we quantized. But he pointed out that there are two ways of interpreting this algebra. Either you just interpret it as the fact that, you know, X and P are the canonically conjugated variables in momentum, in phase space. So it's just a symplectic structure. But there's another way of interpreting it, which is that we might recall that P is also the canonical generators of translations, which, by the way, is the reason why in mathematics, the generators of transformations, obtaining the generator of transformation is called finding the momentum map, namely finding what is the momentum associated with your transformation. If the transformation is translation, well, the momentum of translation is the momentum itself. This is why mathematicians call this a momentum map. So what Isham stressed was that maybe one should not try to quantize the CCR. One should look for what is the transitive action on the configuration variables and quantize that, which in this case, the transitive action is the action of translations, but in the case of a non-abelian gauge theory, the transitive action is the action of the group on itself. And this is the left or right invariant action. So this was before the construction of these variables, but I think it was very instrumental for people to, it was an idea that was very useful to people to keep in mind while deciding to make this jump and give up the quantization of that algebra and insisting on quantizing this algebra with this motivation of Isham, but mainly, as I said, the motivation that then we can use a background independent scalar product. Okay, how about E? Okay, so if we have these brackets here, now we would like them to close, meaning that we would like the Jacobi identity to be satisfied. And you can see that HL1, HL2 equals 0, which is something that follows immediately from that definition of the bracket, is also compatible with that bracket in the Jacobi identity. Namely, so if I now do H1, H2, E on some surface, plus the cyclic permutations, notice that this bracket produces a C number. This is a generator in the algebra, but from the point of view of the phase space, the phase space is just a C number. So it produces something that is only proportional to the connection, and therefore this is proportional to the connection, and therefore it will commute, no matter where S is, right? Even if I have to use this more complicated formula, E fluxes never appear, so this will be proportional to h, and therefore this gives me 0, and this is consistent. But E is not. This is the big surprise, is that if I now look at E on two different surfaces, and we ask, can this be 0? This violates necessarily Jacobi, and you can see this because now, when I do H, E, I, S1, EJ, S2, plus cyclic permutations, here I would have what? Let's say EI, S1, EJ, S2, H, and then EJ, S2, we're going to see something fun happen. H, E, I, S1. So we want to know whether this can be 0 or not, if this is 0, for instance. So let us look about the things that we know how to compute. For simplicity, let's assume, for the sake of this calculation, that let's say this is S2, and H is on a link that starts on S2 with the right orientation, so that at least for this guy, I can use the simplest formula, replace this with 1/2 to J H. Yes, in that order. Now I want to compute E with H. So again, if S has nothing in common with H, then I will get a 0 bracket. But I'm only after now a contradiction with the possibility of satisfying Jacobi while this is 0. So let me take simplest case again, that also sigma 1, just for the sake of showing the contradiction, let's say that also S1, touches the link at just one point. So then I can use twice the same simple formula. And so what is that going to give me? Recall that this is a C number, so the Poisson bracket doesn't see it, so it comes out. And then this acts on it, again from the left, because of my choice here. And so the result of this double bracket is 1/4 to J to I H. Let's do the same thing here. Well, this, notice that is going to be a minus sign because now it's HE. I hope my signs are right. Oh no, my signs were all wrong anyways, because that was HE. So this was minus and this becomes plus. And now this is plus, and it's to I, okay, H. And now when I act with this one is EH, so it's minus. So it's minus 1/4 to I to JH. So something funny has happened. I have reproduced the structure constants of the group. So I have that if I want to satisfy Jacobi, this thing here has to be, well, now I won't be, yeah, maybe we can get the sign. Well, up to sign, this thing has to be equal to the commutator of 2I and 2J is action on H, okay? So let's say this whole thing. So you see that this Poisson bracket cannot be 0 if I want to satisfy Jacobi already in this very simple setting. In fact, it turns out that if S1 and S2 have no points in common, then they will commute. Then it's consistent with commutation because, you know, one of these Poisson brackets here will give 0 if there are no points in common between S1 and S2. But if there are points in common between S1 and S2, it's inconsistent, so this cannot be 0, because otherwise I would violate Jacobi. And in fact, it turns out that the only way to close this algebra, so no, algebra only closes closest means satisfies Jacobi. If this is not 0, but it captures the structure constants, how should I, well, again, I would have to make, different cases as I did there. In the simplest case, if S1 coincides with S2, I can just write epsilon ijk, which are the structure constants, E, K, sigma. In the other cases, I will have, to introduce, spell it out. But the key point I want to make is not so much the detail of the calculation, but is the fact that the structure constants appear here. And now, well, it's not that they appear, it's that we need to have them there. We need to have a bracket that gives such a result, otherwise we cannot close Jacobi. And so now, there are two ways to justify this. One is that. So you say, because now the point is, how can this be compatible with the fact that the point-like Poisson bracket was given 0? We still have that EX at the continuum level should give 0. So one way to justify that you would like to use this algebra is that, namely, that as you pointed out, the smearing we've been naively using here is inconsistent because it's not a gauge invariant, it's not well defined with respect to gauge covariance. So if you do it properly, you see that this adjoint action depends on the holonomy. And so the fact that E does not commute with E is kind of natural because this smeared E depends on A. And in fact, you can now do, that's a complicated object, but that calculation has been done in one of the papers, the founding papers by Tiemann, and showed that effectively you recover this result with the structure constants. There is, however, yeah?
Flash hot water company with there is not an intersection between S and S2. With these two planes intersect in line. What's the structure of the result? Is it or is it?
Let me think about it and get back to you. You mean like for instance, if this is S1 and let's say S2, okay, I'm drawing it horribly, but let's say they have one line in common. Yes. Yeah, I will have to check what happened in that case. There is actually, I would like to give you a more intuitive reason that is due to Alejandro Perez and Alberto Cattaneo and touches on the discussion of surface charges that we had last week, because you will realize that these smeared fluxes are also the surface charges that we were talking about for the Young-Mills case, because what we are doing is that we have this E. Let's say if we were just in gauge theory now, Young-Mills. So I forget about the densities. So we have these fluxes now. So to come back to your point, now I can make them gauge invariant by contracting with, let's say, some gauge parameter. So I could put the trace here. Okay, and then again, let's just write dSA for the volume element, okay? So this is actually the surface charge from Nether theorem. And now you can give a very nice intuitive argument of what's going on, because you would like to connect to a three-dimensional object, namely a three-dimensional smearing as we usually do of these distributions. Can we do that? Well, what we can do is that, so this is, our surface. It doesn't need to have a boundary. Sorry, it doesn't need to be closed. But we can always think of this as let's say, a patch of, let's say, a two-sphere. Okay, so this is a patch, this is Europe. A patch, or Czech Republic there, a patch of the two-sphere. Then I can write that this is equal to the integral on this two-sphere, on the whole two-sphere, of some extension of this lambda, where the extension is defined such that this is 0 outside of S, right? Trivial manipulation. But what's nice is that now I can apply Stokes' theorem and say that this is equal to the integral in the ball of d trace of E lambda, sorry, let's just, this is the Hodge dual of a two form, so let me think of this as a two form and then I apply Stokes' theorem in form language. Okay, now I can use Leibniz and write this as dA, the Young-Mills connection, so trace of dA E lambda plus trace of E dA lambda. But now I can use the field equations. This goes on shell to 0 on shell. And so what I'm left with on shell is the integral over the ball of trace of lambda. It's a simpler way of getting to the same point made above, namely that if I want to give a gauge invariant or a gauge covariant, this would be a gauge covariant interpretation of this flux, namely you see I smear it now with some parameters, so this is gauge covariant. Then when I compare this with a three-dimensional quantity, is necessarily something that depends on both E and A. And again, from these now, you can compute such bracket. Maybe from this formulation, it's easier to answer your question. You see that from this formulation, probably what you're going to see some distributional. So you're going to have an integral over that one line. What do we call it? And let's call it E for the intersection. Maybe, but this should be checked. Maybe good exercise for the students. Integral over the line of lambda, so smearing of E with lambda 1, lambda 2. Sorry, this should have been lambda 1 and lambda 2 here. Yeah, probably it might be something like this, to be checked. I'm not sure.
One thing which I wanted to ask you, when you ask this commutator of this fluxes or this ER in AG, right?
Here?
Right.
Yes.
So this should be valid for arbitrary S1, S2.
That's right. Yeah, absolutely. So far, you see, we're not yet at the level of the quantum states. We're going to get there in a second. So far, it's just a smearing. So if I choose to smear two electric fluxes on surfaces which have nothing in common, they will commute, Poisson commute. But if I choose to smear them on surfaces which cross, then there will be some non-trivial right-hand side, some non-commutativity. Okay, and this was to argue what is the origin of this non-commutativity. The key point is that if I choose my smearing surfaces to be very small and very close to the origin, the source, or the target of the link, then the algebra of smeared functions in that smeared fluxes in that very special case, it will be something very simple. Given by this, which we have already encountered, was a piece of that, but now we actually realize that we have all of this, because we also have the structure constants that appear if, again, we make these hypotheses here. So yes, yeah.
The last argument there, you said that it's integral intersection.
Yeah, I'm not sure because I'm not sure what I should integrate over there. So that's why I'm putting a question. Maybe something like this.
Yeah, because it is not two-dimensional.
That's right. So that's why I'm saying I'm not. It's part. I'll look at it, or some students will figure it out. But it's when the intersection is not the same thing as the surfaces, or is not just one. So the simplest cases is when it's just one point, as in the example there, or the surface actually match. If it's more complicated like this, I have to look. Okay. So now that we have talked about, this was discussion of the Holonomy flux algebra. So now we can connect with what we said on Friday, namely that those cylindrical functions you remember they were elements of L2 of G power the number of nodes. So those functions I had, let me write it again. So some f of G1, GL holonomies. These are square integrable with respect to multiple copies of the R measure. And these carry a representation of a special set of that algebra, which is the one in which all the sources, in which the surfaces are associated with sources or links. Because remember, carry representation of the quantum version of T star of G, which we wrote as G and G commutes. So this was at the classical level. At the quantum level, G and G commute, and then we had Li, Lj, maybe an I, let's say, and then we had Li commutes with Rj. This was very important to understand why in the momentum representation we had Lz and Rz, and then we had something like this acting on the holonomy is the right derivative, and therefore I have a factor of minus. So G to I and R G is the left derivative, and therefore equals to I G. So you see that these functions will carry a representation of a representative of the algebra of holonomies and fluxes, and this is actually what we call the holonomies and flux algebra. That simple representative there, and the key non-trivial result is that that simple representative there is enough to reconstruct a full continuum limit. This was this result of Ashtekar and Lewandowski. If you take the limit, so let's say, let me call this H gamma. Gamma is a graph that is made out of L links. Then the limit for gamma that goes to infinity with the notion of cylindrical consistency embedded in, namely this is an inductive limit. I will explain in a second what it is. Consistency. The limit of this defines a space of square integrable functions with respect to a certain measure that is constructed as the Cauchy completion of the limits of these R measures, a space of generalized connections because they can be distributional and not just smooth. And what is meant by cylindrical consistency, now that we have done the Peter-Weil theorem, is basically the fact that, you remember, cylindrical consistency is simply the property that I can do this limit, namely that I have a graph and I can trivially embed it in a finer graph. So that's the requirement that I can always find a trivial representation, let's say J equals 0 in our case of SU2, such that the link does not contribute to any operator. And why this is true? Because you remember that the Peter-Weil theorem told us that we had these Wigner matrices. Oops. But one property of these Wigner matrices is that D0 of 0, 0, because then the magnetic number has to be 0, is G, of G, sorry, is 1 for all G. Okay, this is how you mathematically implement this cylindrical consistency, and what it allows you is to stack graphs one on top of the other, basically, and take this continuum limit. Okay, but this is not spin networks yet. So the next thing that we have to do is to talk about gauge invariance. But before talking about gauge invariance, let me just maybe already now mention some of the operators that one can have here. So these are the basic operators. These are the simpler operators, the simple operators. Sorry. Whatever other operator wants to work. Oh, right. And you see, what is the interpretation of this operator? So the operator G is the quantization of this quantity here. Okay, so it's the hat of this. What is this operator? Up to some, factors of 2 or Planck length, numerical and dimensional factors. This is okay. Remember that this algebra is associated to each link, and these are oriented links. So this operator is the integral on some small surface which is associated with the source of the link. Maybe I hope it's not too bad of a notation. Was it the source? Yeah, it was the source. R is an operator that is associated with a smearing of the electric field on a small surface associated with the target of the link. Okay? So here is our link. We can imagine that we have some surface here, some surface there. And why are these simpler operators enough to get the continuum limit? Because the continuum limit will consist in things like arbitrarily refining this graph, which means that if I have a surface here, I can always think that actually there is a new node there. The graph is refined by splitting it, adding all the nodes I want, bivalent trivial nodes, such that the surface is very close to the node. This is why this procedure of cylindrical consistency works, but only works for compact groups. So this is more general than just SU2, but requires compact groups. And you see there why, because this procedure here, this arbitrary splitting of a link into many pieces of a link with bivalent nodes, if I have non-compact groups, at some point I run into troubles because I have to do some, at the gauge invariant level, I will have to do redundant integrations over the gauge orbits. If the group is compact, that gives me no problem. If the group is non-compact, it doesn't work because you get infinities. So remember when we had this list of possibilities, I want it to be real, I want it to be commutative, I want it to be compact. I'm saying this because you see why all of those requests are important in the construction, and select uniquely this, for the time being at least, this real Ashtekar-Barbero connection as the only way in which we know how to construct fully the Hilbert space.
Could you explain more
Yes.
why this integral over some surface?
Yes.
Somehow,
The surface was arbitrary to begin with.
it wasn't distinguishing between source and target in the definition of this integral.
Yeah, it did. You remember?
It was only when it was interaction with the
Yeah, so what you remember, it was the grasping. So you have the holonomy, and you break the holonomy, so wherever you're acting, your surface is here. Cuts there, let's say in just one point. So the result of this is that you split the holonomy in two, and you have a grasping there. So it's not, the result is not written in terms of the initial holonomy, because it's now written as the product of two holonomies with the generators inside. Okay? However, if this intersection occurred, so this link was oriented, because otherwise we cannot talk about holonomies. If this intersection occurred here and there, then the action was simpler, and it reproduces the same initial holonomy multiplied on the left or on the right by the generator.
Yeah, but we are suggesting that this L and R is corresponding to some to the flux, essentially.
Well, no, that is not that I'm suggesting it, that I'm just looking at the math. So, you see that algebra up there of the Poisson bracket. You see that algebra is reproduced at the classical level, only the last two steps, not the first two, only the last two, are represented by, so if I go back there, and I restrict myself to S being very small close to the source, or very small close to the target, then the algebra is simply given by 1/2 tau H or minus 1/2 H tau. And this coincides, notice that this is an element of L2 of G on that link. And I simply observe that this coincides with the algebra of left and right invariant vector fields. Here. I look at this as an element of this, and I say, but this Poisson bracket is representing a certain action of vector fields. You know, like when I say that, but XP actually is the Hamiltonian vector field associated with P, now hat for vector field, I don't know, X, the Hamiltonian vector field associated with P acting on a horrible notation also, I'm sorry. You see what I mean here?
I still don't understand how the flux itself can, where it takes these two different positions, and this source and target. I understand that it is in the bracket, but it is interactive.
So, because the flux is associated to the link is oriented. And the flux is associated to a surface. If that surface does not intersect with the link, the action is zero. If it intersects with the links, it breaks it in two and puts the generator inside. Now, if I move this intersection closer and closer to the origin, this holonomy becomes smaller and smaller, so to speak. And in the limit in which this point is actually coincides with the source, there's nothing more to the left.
Yeah, when I have a link, I understand.
Okay, so just one link. I'm just talking about one link for the time being.
But until I had this situation that Li is something that's the order. Like, it's essentially this flux. Yeah, and on the, in this expression, I don't see the link. Yeah, it is just.
No, fair enough. No, very good point. Okay, thank you. Where is the link? Because, okay. Okay, so let's look at it from here. I have just one link, this link here. And so I'm looking at functions which are square integral with respect to G. So I have the link here. And I'm looking at functions of G, where G is just the holonomy associated with this link. Okay? This algebra now, what is the semi-classical limit of this algebra? Is T star of G, okay? And T star of G, remember that it's G times the Lie algebra, where the Lie algebra can be interpreted either as left invariant or as right invariant vector fields. So it is me that now makes an identification and decides how to parameterize this cotangent bundle here. And so in particular, I can, forget about the right invariant vector fields. Let's look only at the left invariant ones, okay? Then I see that what this algebra contains is simply GG equals 0 and G left invariant vector field equals, left invariant, which one was this? This, okay? Then I say, so this left invariant vector fields provides me with a representation of the electric flux, but not any electric flux, only the electric flux smeared on a surface at the source. Okay, so this provides a representation, for the moment, provides a representation of holonomies, and also only those holonomies on L, holonomies only on L, holonomies on other links, I don't have a representation for it, and only those fluxes that are on some surface which is, very close to the source. So it's a very special subset of the very complicated algebra. But now I say, okay, but that was just one choice. I could have also chosen to describe the same algebra using right invariant vector fields. And actually, I know that I need to use them both if I want to understand the Fourier analysis. And I say, okay, but that's good, because that means that I also have a representation for those fluxes which are very, very close to the target. But now you should ask, how about a representation of those fluxes which are neither here nor there? How about a representation of a flux that is there? That object that is not represented by T star of G. Let's be clear about that. That object is not represented. Nonetheless, I try to argue, and there's this very mathematically dense proof made by Lewandowski and then by Tiemann also, that because of this arbitrary splitting that you can always do, it is enough to consider only the special case of the algebra. So, in other words, if you look with only one fixed graph, you cannot describe an arbitrary smearing of your operators. You can only describe a smearing of the operators which is adapted to that graph. That is why this is also called sometimes a regularization. You take a state, which is given by a certain graph, and now some of your operators can be regulated to have a well-defined action on that state. And these are the ones. If you're interested in an action of operators which are not the simple ones on that graph, either you can use cylindrical consistency, refine the graph, and bring yourself to simple operators, or you have to use complicated functionals of these things. Okay, so this is important because it's where this distributional nature, remember in the talk I gave on Thursday evening, I mentioned there were these three aspects of the discreteness: the gamma, the incompatibility, like in Heisenberg principle, and the discreteness of the spectra. Here we're seeing heavily coming into play this aspect of discreteness, because the states will be defined in terms of graphs. You should think of these as, also in Fock space, the states are described in terms of a finite number of particles. And, if I give you a state with n particles, then it's easy to talk about the momenta of these particles. But suppose that now I ask you a very complicated question that concerns an operator that is built out of a smooth distribution of a scalar field. Then understanding how such an operator acts on a space of n particles can be a very cumbersome question. So what makes the situation more complicated here is that we're talking about space-time, which is something for which we are used to smooth to a smooth description. And so that's where this jump is important to accept or not accept.
You are concerned correctly that if you take graph and you are asking, I ask what operator I can have on this graph nicely represented. It's only when the surfaces for this test goes through the vertices of the code.
Exactly. Those are the simple operators. Other operators, either you bring them back to such simple ones by cylindrical consistency, or if you cannot do that, they will be complicated and messy. Okay, so $20 I have? No, what time is it? Is it 7:20? Okay, good. So next part, let's talk about gauge invariance, which you will see will be easier and more fun, more relaxing. That there was a technical, delicate step. because we will be talking about things that you have learned in your first class of quantum mechanics, which are the singlet states in quantum mechanics. And now this is risky because when we started talking about singlets with Tom earlier on in the afternoon, somehow after not even 10 minutes, we were talking about consciousness. I don't know how that happened. I hope it doesn't happen here again, because otherwise we will be sidetracked. So gauge invariant states. Yeah, so let's start with an example. We had, remember we had the holonomy from X to Y. So I'm using notation G to remember there is a group element. And how does this transform? Thanks to the path ordering that we did, this has a simple transformation rule under gauge transformations. The gauge transformation that I do outside of the path have no effect, but also the gauge transformation that I do along the path have no effect. And so the result is simply some group element. What should I? If I write this, is it confusing or is it okay? See, this is a different group element than this. This is the holonomy between X and Y. This is some arbitrary group element that gives me the gauge transformation of the source, and some arbitrary group element that gives me the transformation of... Okay, let's do that. I knew this G of X, Y had a short life. Killed already. Very good. Okay, so how do we make this gauge invariant? We said Wilson loop construction was that if I take a closed loop, the first thing is to take a closed loop so that X is equal to Y, then for these two group elements are the same, and then second thing, I take the trace, because then I can use the cyclic property, bring this on the left, it goes away, and the thing is invariant. But let's now have, so this I constructed it because I knew that the trace would work. Let me now give you a constructive procedure to obtain gauge invariant quantities, and this is group averaging. Group averaging sounds like something fancy, but it's really something very, very naive, very, very simple. Imagine that you have a function of X and Y, and you want to make it invariant under translations in Y. So of course we know that, make it invariant under translations in Y, I don't know, take f of X and Y evaluated in 0 once and for all. But the way to extract something that is invariant under translations in Y is to integrate over Y. And of course you see that if the domain in Y is unbounded, this gives us infinite. But if the domain is compact, then this gives us a function of X, which clearly is invariant under translations in Y. So this is group averaging for you, in short, and you see why it works for compact gauge groups and not so well for non-compact gauge groups.
Sorry,
It also... Yeah.
Under the translation in...
Why?
But
Because it doesn't depend on Y any longer.
but you are
So,
claiming anything to X.
I'm claiming what?
To X.
No, I'm making no claim about X. No, this is what I wanted. I want to construct a function invariant under Y translations, it means this, and I got it. You also see that it works because we're not mixing, X and Y, otherwise it would be more complicated. But so this is the idea of group averaging. I can do it, So how do I get something that is invariant under rotations? Well, you take scalar products. But another way is that you look at the functions that are invariant under integration on the sphere. That also gives you quantities that are rotational invariant. So let's see how it works in this example. Of course, it only works because we have a measure in our space of symmetries, but that we have because it's the same R measure that we already talked about. The R measure is nothing but the uniform measure in the space of on the surface of the Lie group. So group averaging for this loop, the loop we still need, because if we don't have, otherwise it cannot work. So let's assume that we're already with a loop. And then group averaging, that means that the function, which is a function of age, has to be equal to the integral of the gauge transformed function, which is, we said, a function of g, h, g minus 1. These two g's are the same because I'm on the loop. Okay? If I am not on the loop, you will see that it cannot work. But because I'm on the loop, it is the same function. This is the gauge transformation. I'm integrating over all the gauge orbits. Okay? Let's see what happens. I use the group, the Peter-Weil theorem and the group representation property. And so this I can write as sum over jmn, psi jmn, jmn of g, h, g minus 1. Next, I use the group representation property. This I write as sum over p and q, dmp, g, forget about j, is going to be the same everywhere, pq, h, dqn, g minus 1. Next, I use the fact that the group is unitary, so the inverse is equal to the transpose and conjugated. So this is equal to this. And so what I have to do as an integral is various sums, j, m, n, p, q, the Fourier weights, or g, it doesn't matter where I put that index. This guy comes out of the integral, and the only integral I have to do concerns these Wigner matrices, mp of g, and what is it, nq bar of g. Now the Wigner matrices, you remember I told you they were Fourier weights. So as Fourier weights, they have the nice property of being orthogonal. They provide an orthogonal basis. Notice I'm saying orthogonal, because it's not orthonormal, it's not an orthonormal basis, I'm sorry. And in fact, the result of this integral is 1 over square root of 2j plus 1. Notice that this is the dimensionality of the vector space, delta mn, delta pq. This is called the orthogonality relation satisfied by the Wigner matrices. You don't have to compute it yourself. You can find this in books on the theory of angular momentum. But then look, what is this delta pq doing? Delta pq contracted with dpq is giving us the trace. So you see that what we obtain from this is sum over j of psi j. It also gets contracted, jmn delta mn, and then the trace. Now for the trace of a representation in the literature, people use this character, this symbol chi, and this is also called character. And in fact, this Fourier expansion for gauge invariant functions, you see that this is an expansion in terms of characters, and so sometimes it is also called the character expansion. But it's only for gauge invariant functions that the expansion is in terms of characters, because the characters are gauge invariant functions because they include the trace. More in general, you will have these Wigner matrices as weights. So now that we have seen how to recover these using group averaging, now we can start to have fun and play with different graphs, do something a little bit more interesting than just a single loop.
So how can you introduce something a little bit more complicated even? Because now you were doing loop.
Exactly, that's what I want to do. But I want to do something more complicated than just a stupid loop. Yeah, exactly. No, very good. But you see, I couldn't do it randomly as I guessed that the trace would work. Now I have a procedure that is systematic. I can apply it to an arbitrary graph and see what happens. And spin networks is what happens. Just to, there's no suspense. So So what's the next?
But
Yeah.
basically, what will happen is that you will reduce the number of, or the set of such
Objects.
objects.
Yes, exactly. You see, I've already reduced it here to say that if you want to look at it in the Fourier dual space, you only want things that depend only on J and not on J, M, and N. Think of these SU2 invariants as invariants under rotations. Clearly, you don't want things that depend on direction. M and N, you remember, are magnetic numbers. So if you think of this as an SU2 problem, M and N, M is the projection of the angular momentum in a certain direction. So things that depend on M and N explicitly, they have no chances of being rotational invariant. Okay, whereas things that depend only on the modulus of the angular momentum, which is J.
But that's fine, but it means also that you're losing, I mean, so definitely you will not explain full theory using just spherically symmetric solutions, right?
Well, except that in this case, it's not spherical symmetry they were talking about.
No.
It's this internal gauge. And therefore, you do want to only talk about gauge invariant quantities. Because you're not talking about the global gauge, the global,
Yes.
okay, spherical symmetry of space-time, yeah,
Yes,
right?
that's simply you want to see the
Exactly. And you might think that, you know, the only gauge invariant quantity is scalar products. No, it's much richer than that, the space of gauge invariant observable. So what's the next simplest graph? I give you just one more line.
I thought you will put sphere, for example.
Sphere is not a graph. We're only going to work.
Yes, but that's what I had in mind was you can put cube, for example. But I mean, yes, cube.
But sure. But then my graph will be the boundary of the cube. Yeah, that I can do.
Yes.
But it has to be a one-dimensional distributional smearing, a graph. Okay? So this is a little bit more complex. I can do this if you want, but I wanted to do something simpler before getting there.
But what I had, when I asked you, I really had in mind three-dimensional. So basically,
but this loop is embedded in 3D.
So what I had in mind was that you are integrating over all trajectories which are between x and y, and you will still keep the invariance. I mean, basically by integrating over all.
No. So this graph or line is embedded in 3 dimensions. And what it represents is a parallel transport along that fixed line. I don't want to change that line for the time being. Changing that line will correspond to the invariance under diffeomorphisms. We'll talk about that later. For the time being, it's just embedded this line or that graph is embedded, and I'm not touching this. However, the variables that I'm associating to such a graph are non-gauge invariant variables. So what I would like to know is to take this Hilbert space of non-gauge invariant functions associated to a certain graph and make them gauge invariant. And the first statement is that if the graph is open, like in this case, I just cannot.
But you can do the same.
I'm going to do the same here. Yeah, sure. But what happened? Yeah, of course. Yeah, absolutely. Absolutely. Yeah. So what we'll see in that case is that suppose that your graph has some complicated structure, but then there are open legs. You will find with this procedure that everything is gauge invariant here except at the open legs. The open legs will be where your gauge invariant is broken.
It will not be, you just show that your function is trivial.
Or, that's right. So either you accept to break or if you insist on not breaking it, then the function has to be trivial, absolutely, yes. No, so the next thing that I wanted to do was this. I take the loop and I cut it, okay? You remember that, changing the loop by this, we will not be interested in, because at the end of the day, diff invariance will get rid of that.
What about 8?
Sure, I can do 8. We can do it. Let me do that first, and then because this is very interesting, but let me do this first, so that I can...
You can make flowers.
Yeah, you're kidding, but there are papers that are called flower networks.
Really?
Absolutely, yeah, because in fact, loops capture the gauge invariant structure, and therefore, playing with diffeomorphism, you can effectively reduce the graph. If you know a little bit of graph theory, you know that there are homomorphisms that allow you to map graphs with a certain number of internal loops into structure like this, provided that your node here codifies the maximal tree, you know, this notion of maximum. Well, let's talk about flowers later. Let's do that. It's a simple exercise. Now we have 3 different links. So we have 3 different holonomies, so we're calling them H. So we have H1, H2, and H3, and we have 2 different gauge invariants, and it has to be oriented. Let's say that we orient it like this for simplicity. Then I can tell you what happens if you change the orientation. This is the node 1, so let's say there's G1 and G2. Okay? So what I want now is a function of H1, H2, H3, which satisfies this property. G2. Now they're different. So you see, according to the logic of just taking the trace, I have no hopes of making this work. Sorry. G1, H3, G2 minus 1. However, let's not lose hope. We do exactly the same procedure. Okay? So this function, I'm going to write as sum over, you know, ji, mi, and I, where I equals 1, 2, 3. It's going to have all the Fourier weights that she needs. And then there will be 3 Fourier modes for the distinct holonomies that this function depends on. M3 and 3 of H3, J3. I'm already going ahead and, you know, okay, this will be on the left-hand side. I do the same thing on the right-hand side, and then I use the group property, the very same equation I used here. Okay, so those M and N I opened up, and I use these P and Qs. So integral of dg, so this is not, so this is equal to the right-hand side, integral dg1 dg2 of d. Now one has to be careful about the indices. Let's say, sorry, this then have to become P and Q. P and Q, and then I have P1, no, M1, P1, sorry, M1, P1, G1. Then I have G2. Let me forget about G2 for a second. Anyway, I'll put it here. I'll put it later. Then I have D, M2, P2, G1, M3, P3, G1, and this is J3, and this is J2. And then I have the same thing with G2 and different indices. N1, no, Q1 and 1, G2, and so on. But they factorize these 2 integrals. So this is the equivalent of our, earlier on, it was a single integral and it was orthogonality condition. Now what is this? Well, let's interpret this orthogonality condition in a different way. From the point of view of group averaging, this is telling you, I give you 2 tensors. So this you know, like, you know, you can think of Jm as a vector. This is a tensor now. And I'm telling you, what tensors can you build that are SU2 invariant? That's what this integration is doing. So these are tensors with 2 indices each. So in a sense, you can rephrase this question by saying, if I give you 4 vectors, how can you build a rotational invariant out of 4 vectors? If you want, it's a super simple question. There's only one way. You take the scalar product between one of them, between any 2 pairs. And that's in fact what this is giving you. See, these are the scalar products. Notice that if I'd asked you, what are the invariant ways of, rotational invariant ways of coupling 3 vectors, you would not have used scalar product, you would have used the mixed product. If I give you 3 vectors, you would have said, you know, Vi, Wj, I don't know, Uk, epsilon, ijk. The triple product, it's also a rotational invariant. So what you get on the right-hand side depends on what you're integrating over. So this integral is asking the question, what is the invariant object that I can build out of the tensor product of such representations? And who remembers how to describe gauge invariant, rotational invariant combinations of tensor products? Maybe I'll take another. Let's do first the example with vectors, and then we'll move on to tensors. It will be very easy. Let's first quickly remember how one does it with these quantum vectors. So if I give you two vectors, let's say J1, M1, I take the tensor product. So this thing, it sits in the tensor product of these two vector spaces. And if you remember your theory of angular momentum, or let's specialize even further, so maybe it helps your memory. Let's say that J1 is 1/2 and also J2. So this state is just, 1/2 M1, 1/2 M2. You remember that, for instance, if both spins are going up, so let's say if this is the state plus, let me write it for short, okay, let's say 1/2, 1/2, 1/2, 1/2, and we can write it for short as plus plus, where this just represents M1 and M2, then you know that this state is also as total angular momentum 1 with magnetic number 1. And if you take the state plus minus, plus minus plus, and you normalize it, you get total angular momentum 1 with magnetic number 0. So this is a state that is up here, whereas this is a state that is all spread here in the xy plane. And if you take this guy, this is the most interesting guy, you get the so-called singlet, which is the global SU2 invariant state. By global, I mean that this state satisfies the J defined as J1 plus J2, the sum of the two operators, acting on it is 0. Total angular momentum is 0. Now, when I explain this, usually I get the question, how can that be that the total angular momentum is 0, since we know that J has components that don't compute among each other? But let's not forget that the statement that you cannot simultaneously diagonalize non-commuting operators is a statement about diagonalizing. So it means you cannot find a complete basis in which that is true. This is just a very special state. You can always find one state in which non-commuting operators, well, always. There are situations in which special state exist. Okay? So the total angular momentum, not just Jz, is 0 on such state. And we can also reverse and therefore say that when I couple these angular momentum, these two angular momenta, I can choose a different basis that is given by, so here, the basis of commuting operators is J1 squared, J2 squared, J1z, J2z. I can change basis here and use J1 squared, J2 squared, and then total angular momentum squared, and total angular momentum component z. This is what I'm doing here. So I can change basis and use J1, J2, Jm, and the change of basis, it's uses a letter C, it's a sum over M1 and M2, and the notation is J1, J2, J, M1, M2, M, and here we have J1, J2, M1, M2. So this matrix of change of basis is simply, in this case, 1, 1/2 plus 1/2, 1/2, sorry, 1 over square root of 2 minus 1 over square root of 2, just these coefficients here. These things are called Clebsch-Gordon coefficients. And there are two useful ways of interpreting them, either as, this coupling, you can decompose it, thanks to that, into, sorry, when I look at the way around, now I'm looking at the way around, I can decompose it into irreducible representations, which is what is happening here. You see, this representation is reducible, but because it's a tensor product, so by definition it's going to give you a priori something reducible, and it splits this tensor product into, so if we go back to this example, we have 2 by 2 tensor product 2 by 2, so that gives us some 4 by 4 representation, which turns out to be possible to diagonalize it into a singlet and a 3 by 3 representation, okay? So it gives you the decomposition into irreps. And this J goes from, goes from J1 minus J2 in norm to J1 plus J2. So in this example, from 0 to 1. This is one way of interpreting it, but you can also interpret it as a map from the tensor product of 3 representations to the complex number. And when you think in these terms, it's called an intertwiner map that tells you how all the possible gauge invariant ways or rotational invariant ways in this case, then the irreducible representations can be intertwined.
Sorry, say again, I didn't get it.
You can also interpret this map either as those coefficients that appear, that's clear. The alternative way of thinking about it is that you can see this as a map from 3 tensor product of 3 representations into the complex numbers, the coefficients. You see, you look at this. You feed me 3 irreps, 3 vectors, and I give you a complex number. That's just a trivial statement. That's what I'm saying. You can look at this, as a map. It eats irreps, vectors, and spits a number. Okay, but it's useful to see this. Maybe I can give you a graphical.
I mean, for this first interpretation, we all know it very well.
Right.
We went through many times, but
this is so.
Can you give an example? I mean,
sure. Let me give you an example of that. Let me take here 1/2. Sorry. Let me take here 1/2 of 1/2. 1/2 of 1/2. 1, 0. I feed these 3 vectors in my map, and I get 1 over square root of 2 out of it.
there is minus missing somewhere or not? The one,
Maybe.
the first 2 are the same, right?
Which? Yeah, that's right. Yeah, absolutely.
Yeah, so 3 vectors. Okay.
Right, absolutely. Yeah, something like this. Okay. Now, this is useful because, so something very useful when you do this analysis of quantum angular momentum is the so-called graphical method. Which, if you never encounter, it's very convenient. And you represent each vector, each ket, as an arrow. So this is the J1, M1 ket. This is the J2, M2 ket. This is the intertwiner, the Clebsch-Gordon coefficient, that tells me which weight will come out of here, which I'm calling Jm. Okay? That's the Clebsch-Gordon coefficient. It tells me that I can recouple 2 such angular momenta and get a third one if J and M satisfy some specific properties, the usual ones.
So it gives a probability that the state is big.
Sure, not the amplitude, the probability amplitude.
Yeah.
What if I couple a third angular momentum? If I have 3 angular momenta and I want to describe the global state, this graphical calculus tells me, okay, add it here. Okay? Then you will have a new Clebsch-Gordon coefficient here. So these we should call not the total angular momentum anymore. This is the partial total angular momentum. You know, so it will be some state here, but then I'm coupling another angular momentum, so the total angular momentum only occurs here. Okay? And this recoupling, I can do it in different ways. Because the particles are indistinguishable, I could do it this way, or I could couple first 1 and 3, and then couple 2. Okay? So there are different ways of coupling angular momenta. And these Clebsch-Gordon coefficients tell you how you do this at every step. So for the case in which there is a single, the vertex is trivalent, this Clebsch-Gordon coefficient is unique. But if you're coupling 4 angular momenta, the Clebsch-Gordon coefficient, the intertwiner, is not necessarily unique. Look, let's look at an example. I have 1/2 and 1/2. All I can get here is 1 and 0. Okay? But now I couple 1/2, 1/2, 1/2, 1/2. There are 2 possible states here. I blow up this node in any basis I want, because everything is symmetric here. I could get 1 or 0, and it's compatible. So there are 2 possible Clebsch-Gordon coefficients associated here. So last 2 comments, and then we go back to our matrices. There's Clebsch-Gordon coefficients are related to, no, let me go back to, where are the matrices? Oh, no, they're up there. So anyways, just to tell you the result, no, it doesn't matter. So the integral of 3 of these Wigner matrices, so M1, what did I have? P1, Q1, P2, Q2, P3, Q3, gives me the product of 2 Clebsch-Gordon. Why the product of 2? Because you see, these are not vectors, these are tensors. So that's why you get 2. So you get Clebsch-Gordon, J1, J2, J3, P1, P2, P3, Clebsch-Gordon, J1, J2, J3, Q1, Q2, Q3. One of the 2 will be the complex conjugate. Even though for SU2 we can always pick them real, choose the phase convention so that they're real. Actually, if you use Clebsch-Gordon coefficients, unfortunately, you get some annoying phase factors and some square root of J3 plus 1. And so Wigner in the 20s renormalized the Clebsch-Gordon coefficients by introducing what is called now the Wigner 3J symbol. And this is what people mostly used in the recoupling theory of the angular momentum. So these are the Wigner 3JM symbols. They're like Clebsch-Gordons, but they are normalized, and making them normalized give them nice symmetries when you permute these indices, which the Clebsch-Gordon don't typically have. And what if I have 4? Well, so these guys are unique, as I told you, but if I have 4, they're not going to be unique. There's going to be a new sum that appears over all the possible intermediate states. And so if I have 4, I'm going to have a sum over this intermediate state, which depends, its label depends on the basis I choose. You remember I could choose this basis, or that basis, or, you know, the third choice of basis in which I flip 2. And so let's say it's 1, 2, for instance. I have to choose a basis, and then I will have all of these, and these guys now labeled by this additional quantum number. This is called a virtual spin, because you see it's a spin, but it's hidden inside, so it's called a virtual spin. Or sometimes it's also called an intertwiner itself, even though that's a misnomer. This can also be called the intertwiner label. Because you see, in the trivalent case, the intertwiner is unique. In the four-valent case, no, so there is an intertwiner label. But then people get lazy and just call it the intertwiner, even though intertwiner is really this map. Qi, I1, 2. Okay, so with these formulas, we can now solve the problem for an arbitrary graph. Because you see, let's go back to that calculation up there. You see, in that case of that I graph, that integral is going to give us two of these Wigner symbols. One with the first integral in G1, okay? One with m's and one with p's. The one with m's will contract with the Wigner, with the Fourier weight, the analog of the trace we had there. And the one with the p's will contract with the remaining h holonomies. Okay? Same story with the G2 integral. So at the end of the day, the analog of my formula for the Wilson loop for that I graph so the gauge invariant state is going to be C of H I product of I from 1 to 3 of dji m I and I of H I. Sorry, I forgot the Fourier weights. I'll write them at the end. And then product over the nodes. So these are links actually. So product over the three links. So let me use L everywhere. And then product over the nodes, which there's two of them, of such intertwiners. So let me call it E for intertwiner with the appropriate labels. In this case, there will be one node will have all the labels M, and the other node will have all the labels N. Okay, but for shorthand notation, let me just use M here. Or even better, since anyway these indices are all summed up with the indices here, I will just remove them everywhere and write trace. Okay? So trace of this big thing is what replaces the character. And then I have the Fourier modes. And the Fourier modes are the size in which all the magnetic indices Mn are contracted with these remaining Wigner symbols. Just like in the trace example, psi jmn, the magnetic indices disappeared taking the trace. So here I have psi, let's call it, I don't know, psi whatever, some new psi, j1, j2, j3, which is the Fourier mode with all the magnetic indices contracted with the Wigner symbols. And then I have to take the sum over all the JL. And it's nice to write it like this. First of all, okay, this trace is not just a trace of these matrices, uses this combinatorial structure that is associated with the graph. So if I want to know what exactly this means, I just have to draw the graph. I draw the graph again with the orientation, it is important. And then I know how the indices are contracted. When this is 1, it means that I'm here. So I'm going to contract with, let's say, depending on the basis I've chosen here, I'm going to contract, this intertwiner on this side and the other intertwiner on the other side. So the group structure contains the combinatorics, the graph tells me what is the combinatorics that defines this trace. And then you see that this part is the basis. So these are just the Fourier weights, and these are the basis element. That's what we call a spin network state. So in this form, I wrote it. It applies to an arbitrary graph now. Of course, things may get particularly complicated if the graph is very complicated, if it's a knotted graph, if it has 1,000 nodes. But the definition is always the same. It's always this. Tensor product of the irreducible representations associated with the holonomies, in which all the indices are contracted with these intertwiners. And I think that's a good time to stop, because tomorrow I will show you how we have quantum operators that act on these states and endow these quantum labels with a geometrical interpretation. Thank you. Ah, shit. Yeah, I'm late, I'm sorry.
So tomorrow, the lecture will again start at 6:10.
Could you write this expression is
Yes, for that example. There's a very good for that example, we have M1, M1, H1, so this is down, and these are the relations. These are different representations, and then I can type them with two of these little symbols. One, two, three. Now there's a touch, and one, and two, and three. It's a little touch that the contraction should be invariant, so a priori the biggest symbol associated with all outgoing vertices is different from the one associated with incoming vertices. But in the special case of the invariant one, the symmetry and the arithmetic are the same. Otherwise, we have to be careful whether this is incoming or outgoing, it's a different symbol. For instance, if you click one arrow, you get a factor of -1, j minus 1, delta of m minus n.
so what you denote by I, it is this
Intertwine, this sensor here.
both together.
No, one. Because you see, each one is associated to one vertex, to one node. And this is associated to the other one.
So we
So if I say there's a nodes, there's one per node. Yeah, and we intertwine, now you see why I stressed, let's think of it as a map from three representations to another. So I'm pretty this.
And now, if it will be start, it always starts on, right? So
Yeah, the other one starts.
Still something confused.
Yeah. Okay, apart from the deal of intersection,
No, this the weekend because I saw that I understand this and now I'm a bit confused.
it was a bit fast. So you see, don't forget that you have to impose these two Bayesian values, one per node. Okay? So that gives you two group integrals. Then in each group integrals, you have as many representation matrices as there are links.
Exactly. This expression, where it's coming from the fact that this integral decomposed to two parts.
No. This integral does not decompose into parts.
But you have the C times C.
No, let's read about here. Remember, I know, I'm sorry, in my notes, I knew I had to go through this. That's why I'm confused, because I went too fast and I jumped this. So you remember when I explained the Clebsch-Gordon, you do a Clebsch-Gordon, or even a linear VJ symbol, doesn't matter. Clebsch-Gordon, you can see it as a map from, it's a map from the tensor product of BJs into the complex numbers. And if n is 3, this is unique. Otherwise, you have multiple choices. Okay? But now, we're not doing the tensor product of vectors, we're doing tensor product of matrices. And each of these matrices, you remember, as this structure, but either by. So what we're doing now is tensor product of such tensors. But basically, what happens is that the structure factorizes, and therefore you get a Clebsch-Gordon acting on this, bras and a Clebsch Gordon acting on these scales. You see each of these, let me write an equation which hopefully will be illuminating.
So why it factorize? Why you don't have some mixed terms?
Ah,
4 and 2.
yeah,
So which makes sense? Like when transfer them.
because no, but I can answer that because look, because of what
it is two operations.
So this we can also write as yes, I can do yeah, let's see. So this I can also write it as P1. Let me remove J, it doesn't matter. P1, Q1, P2, G, Q2, P3, G, Q2. Now, let me think for a moment. I think what we can do.
No, there should be Q3, right?
Yes.
Okay.
Now, what we can do, I think, I'm not sure, is that we can write this as dg times d. We can introduce. Okay, let's see. Because this is gauge invariant, I can also put a redundant integration, so I can also write it like this. Okay, let me prove that this equivalence is true. This is trivial because this I call it G tilde. This is equal to G tilde by the invariance of the R measure, and this gives me 1 because it's normalized. Okay, so I prove that they are equal. Now, hopefully with this I should be able. Now I can split this into this. You know, like there would be, this would then have to act. So here there's a product, rows and columns. So here there's a free index. And I want to, I don't know, no, I'm not sure. And then there's the structure with H and Q and the integral over H. And I would like to argue that this is giving me the first Clebsch Gordon, and this is giving me the second Clebsch Gordon. This and this.
So you insert H2 or 3 times, yeah?
Sorry?
You inserted this H2 or
Yes,
3 times.
yeah.
But they're different age, right?
No, the same H on all three of them. But, yeah, I'm not sure.
You cannot.
Let's not try like this.
Guys, sorry, can we postpone it?
Yeah, anyway, these are that you can find in standard books on regarding theory. But there should be pretty reason why you cannot mix up.
But
maybe, sorry, just last try. Maybe because, to mix up a dry and a cat, you will need some map between forms and vectors, which in this form is, right, probably this is the reason why. These are bras and cats, so unless you give me another tensor which maps the two into one another, the integral by itself cannot do it. G, how can G map a bra into a cat? Contravariant vector into a covariant vector. If you want to get mixed things, you will have to do, you will have to do some other.
You have created a metric.
That's right, but that's a metric, so what they will do is to couple forms with forms or vector with vectors. You will need now some.
Metric exactly writes for lower index.
No, metric is. Doesn't rise.
Yes, it does.
So you will need something like
you need exactly metric is for rising and lower index.
right, which means that it's something like this. So you will only couple vectors with forms. Now you like something like this on top of the metric, which you do have, and it's the complex structure. So it's this thing that I was writing before. So effectively, on top of the metric, you also have something that allows you to flip incoming bras and cats. But this is not, I don't want to say something wrong, but I think that this is not part of the group, and therefore this integration cannot do it for you. You can do it by hand to go from the bra to the cat, but you cannot do it automatically with the integration. If I can find a more convincing explanation, I'll...
But you said that when you go farther, that you will have 4Ds or more Ds
Yes.
and make integral. So in that case, you say that there will be some sum over
internal sums, right, over these intertwined labels now.
Yeah.
This is a very...
Which essentially gives you some additional structure, some
Absolutely.
additional tensors which you can add then.
Absolutely, yes. But all these tensors depend on the orientation of the initial graph.
Because in that case, it will not factorize.
You will not factorize, absolutely. Absolutely. In fact, well, it will be a sum of factors, but the whole thing will not factorize.
But just to understand, what is your target? I mean, why you are...
He's wondering why is it so simple?
Yeah,
No, but it's clear this is just example for this. I mean,
No, it's a for graph now.
No, this is key observation, that you somehow you want to write down what is gauge invariant function.
yes.
Yeah, and from that one shows that there is some sum over all possible label graphs.
I give you a bunch of words.
Interesting over through the interviews.
Right, but I give you, I want to know all the possible invariants between forms or vectors, but the only object you can use is this or this.
You know, I understand the result. Yeah, that I understand that you want to take the gauge invariant, so at each vertex essentially you have to cancel all indices. Yeah,
But the fact that you cannot mix the indices, it's important. And
yeah, and for that you have already this invariant tensors which you can modify.
That's right.
But you are suggesting that this follows from this nice averaging over group, which I rather like.
A group that does not include, a group that has a Killing-Cartan form and that's it. It doesn't have also a complex structure in the group action. You can only do it by hand. That's the first observation. And the second observation is that it's associated to oriented links. If the links were not oriented, you cannot distinguish bras and cats, then of course it would be much more complicated. So for a group that doesn't, SU2 is maybe difficult. SU2 is this important property that this conjugated representation is isomorphic to that one, and this isomorphism is given by its quantity here. But for other groups in which there isn't such an isomorphism, you wouldn't even think of this possibility of this.
This one particularly is you have always. It's just duality, but then everyone gets.
No, duality. No, I think for instance for SL2C you don't have this because left-handed and right-handed spinors are different and not isomorphic representations. You cannot identify them. One transforms with one part of the group and the other one doesn't. Whereas for SO2, if you think in terms of what do you call those diagrams?
No, but in that
Like
case,
the 2 and 2 bar are the same.
yeah.
They are isomorphic, but if you're doing SO3 or even for SO3, this is going to be true, right?
Yeah, but there you have some additional structures. Yeah, in SL2C you have this metric form and so on.
Right.
Which essentially
That's right. But once again, you also have some similar thing, namely that it is true that you have an additional structure that allows you to map bras and cats, but it shouldn't be possible to produce it as one of the group elements.
Okay, I don't think I think that the result is correct. I just want to figure out
Intuitively how
much to follow.
Still, this formula is valid only for this graph.
No, this formula is going to be valid for any graph.
No. So you will put here.
You're absolutely right.
No.
I put here
No,
arbitrary number of nodes I put here arbitrary number of
It was the
leaves.
reason why he said
Yeah.
this paradox. Yes.
Yes, but then you have to change also psi, right?
Yeah.
So you will have to change completely everything you want to change. Yes.
But it's clear that what is generalization.
Right.
The important is that you can factor it to this interval. At each vertex you have some quantity which somehow cancel all possible indices.
Yes, but you can. No. What I'm saying is something else. I mean, there you can prove it that this is like this. This is probably trivial. But in general, you show.
Yeah.
No, but we did not show it.
This
This is your question.
But,
Yeah. And
This is not a question. One way is to prove that just intervals are most general tensors which are labeled by different representations and then mix the representation together. Now the second question is that you can decompose it to some more trivial parts which you already discussed.
That's right. This I didn't prove it explicitly because I only, I went too fast.
Here it is, I think, important which group it is. Yeah? And in case,
Absolutely. But in fact, already at this level, it's important which group it is because if you use SU3 now, it's not unique data twine. I don't remember, there's a famous example. For instance, you have these two representations in SU3.
So it's already interval the winners depends on the group and on the winner. And your statement is that for our group, everything can be built just from this three vertex.
No, I didn't say that.
he just limited
No,
to trivial
I didn't say that. If you only limit it to trivial vertices, then these guys will always be trivial. Because we're not in SU3.
I have four vertices that it can be decomposed to this.
Yeah, that is true. But then we produce new labels, which are not here. There's no holonomy in them. They are here.
internal degrees of freedom.
Exactly. There are different types of quantum degrees of freedom. You see, it's true. But then I can always do for any group. I can always do some equivalent of the recoupling theory of the angular momentum, recoupling theory of the SUN. That I can always do. And so I will split this into some, there can be only external lengths not in this vertex. You will do this recoupling theory always in the same way, like this. But these are now virtual spins. In particular, it is true that this sum will include a sum over such labels, but it does not come with an holonomy associated to it. Because it's coming just from exploding this.
So these internal legs or links will not be
here. They are here.
But
so let's do one last thing. The example with the first case in which this appeared, this situation appears, is if I take this instead of this.
They are not dynamical, so it means
I
that
do this. If I do this, now I have 4.
Yes.
1, 2, 3, 4. What do I get when I do the same calculation? When I have the product of the 4 lines. That doesn't change. Okay? But now, when I do the integral over dg1, say here, I have 4 matrices. So what's the result now? It's a sum over intertwined labels. Let's say I choose the basis 1, 2. So I zoom and I do the coupling theory like this.
And my question is it true that for
now, just to finish, what happens now? That this is E 1, 2. So this is now M P, this is E 1, 2. Remember now that half of these were to trace against this, but the other half had to be traced with this part. So what happens now is that when I trace over this part, this sum remains, and this label decorates the Fourier weight. So this is not just a sum over the links, but sum over the spins associated with the links and the intertwiner associated with the nodes. That's why now it is an orthonormal basis. And those are the.
And I really think not that I have to go and I have to thank you, but also, people should come to this. So it will still be on your table. I will show it.
I'm sure. Okay.
But I think that you just said what I was claiming, that the intertwiner can be decomposed to 3 vertices.
Yeah, that's right. But the important thing is that if you do this, some of the links will carry holonomies and some will not. So you have your symmetrical graph, you can expose it, and just make it trivalent. You can. But not all of those links will carry holonomies, and this will give you orthonormal states. This is very important for the construction of the quantum operator.
Well, you will talk about it.
Yes, tomorrow I will explain why this is important.
So,
because otherwise, if everything were just equivalent to trivalent spin networks, the construction of the theory would be different. In particular, the volume operator as it is defined will always be trivial.
Okay, so this should be somewhat clarified in the text.
Yeah, clarified.
see you guys.